we look at the implications of the fact that r squared d theta dt is constant, which again results from any system in which the net force is directed in the negative radial direction, particularly in this case, in the case of a gravitational force of one object toward another. R of t is the vector that describes the position of the object as a function of time. The R of t vectors, tips of the R of t vectors, trace out a curve. R of t plus delta t is the position at time t plus delta t. Generally, we'll think of a short time interval, but in this case we make the time interval a little bit more exaggerated than we ordinarily would. Between clock time t and clock time t plus delta t, the angle theta of the angular position theta of the object changes from one value to another. So there's going to be delta theta, and delta theta is approximately equal to d theta dt multiplied by delta t. D theta dt being the rate at which the angle theta changes, delta t being the time interval between the two positions. At clock time t, the object is at some distance, which we'll designate by little r of t. And at clock time t plus delta t, the distance will be little r of t plus delta t, where we understand that little r is simply the magnitude of the big R vector. Now let's consider the figure where we have a angle delta theta, which we understand to be d theta dt times delta t, and a vector r of t that doesn't change too much in magnitude between 2 points. If there isn't a whole lot of change in magnitude, and there won't be if delta t is small enough, then the distance from here to here, by the definition of the radian, is simply delta r, delta, and that's unfortunate notation, but let's use delta s equals r times delta theta, so that this displacement here has a magnitude that's equal to r times the change in the angle theta. In that case, if delta theta is small, which will be the case if delta t is small, this triangle is an approximate right triangle. Now, the magnitude of r of t and r plus delta t is pretty much the same. R of t and r of t plus delta t don't vary by much, so I'm going to just let r of t stand for this side of the triangle and r delta theta for this side of the triangle. The area of this triangle is just base times altitude. If r doesn't change by much, then both of these angles are pretty much equal, and if delta theta is small, it follows then that these angles are both near 90 degrees, so that r delta theta is very close to an altitude. So we get area equals base times altitude equals r of t times r delta theta. Now I'm using r as shorthand for r of t, again assuming that delta t is small enough that r doesn't change by much. Suppressing the t notation, this gives us r squared delta theta. Of course, delta theta is the change in our angular coordinate, and delta theta is nothing but d theta dt times delta t. Now this is an approximation, this is an approximation, this is an approximation. We could go through the details of showing how in the limit as delta t approaches 0, these approximations approach an exact result. What we can say is that the rate of change of area is r squared d theta dt. Now, formally, if we do the change in area divided by the change in t, we do get something very close to r squared d theta dt, so that taking the limit as delta t goes to 0, and we might write that, that's the limit as delta t goes to 0 of delta a over delta t equals dA dt. So we've kind of implicitly used this idea in calculating this. We see that dA dt is r squared d theta dt. At clock time t, the area of this region here is changing at the rate r squared times d theta dt.